Hi everyone, my name is Philipp Huttner. I'm the business owner for Mike Shi and Mike Plus Rivers at DHI, and I welcome you all to our today's webinar, which is about Mike Shi, groundwater recharge modeling for MODFLOW and FEFLOW. Yesterday we had the live session of this webinar due to technical issues with Teams, and since we had also some issues with the Python workflow, we decided to do a new clean recording. Yesterday, I was accompanied with my two colleagues, Joanna, who helped me a lot with the coordination and setting up and the work in the background. And also Douglas Graham was helping a lot with answering the questions. So we will probably split up this recording actually into several videos, since the 2 hours are hard to digest. And we will start now with the first block, which will be around 40 minutes. We will talk a little bit about the challenge with the non-uniqueness. Then I will give you a short introduction to Mike Shi, but really only a short one, because as you can see, the last block will be the live demo where we build a model in Mike Shi completely from scratch. So I will show you in the first half of this live demo how to pre-process the data in QGIS. And once this is done, how to click together the models. And since we were running out of time yesterday, I will show you this time also a little bit more how the results look like, how you can evaluate them, and then at the end show you also some advanced tools for further steps. So let's start with the presentation. I will then also show you directly the workflow, how to integrate it with MODFLOW and FEFLOW, and what could be the next steps after attending the webinar or after seeing the recording. Now, we all know it, the challenge with the non-uniqueness. Let's assume we want to build a model in MODFLOW, as you can see it on the left side, or a FEFLOW on the right side, or any other groundwater model. The question is where to get the groundwater recharge from. It's one of the most important inputs to groundwater models. Hence, it comes along with the highest uncertainty because it's hard to quantify. You cannot measure it directly. Now, you can treat it in 3 different ways, basically. You can see it as a complete calibration parameter. That means you start with a rough guess, or you take the precipitation, which is multiplied with a factor, or you calculate it externally with a third-party software and supply it as input boundary condition to your model, for example, with GIS-based solutions, or you take an empirical or analytical function. Or you treat it as a third option as a real internal process variable. This is the way fully integrated models like Mike Shi produce recharge. Now, what you can see here is that, of course, the groundwater recharge estimation approaches evolved over the decades. Originally, in the 1960s and 70s, many papers were talking about empirical and analytical methods that were estimating mostly multi-year averages estimates only and no temporal dynamics, but we were far away from daily or monthly values for recharge. Then in the 90s, the GIS-based solutions were trending. They were mainly using conceptual approaches or linear reservoir methods in order to separate the rainfall into direct runoff, intermediate runoff, interflow, and base flow. And today, since the 2000s, the computational performance allows us to run fully integrated catchment models, for example, like Mike Shi. They can really run daily to sub-daily time steps, and they incorporate really a full process coupling. Now, talking about MODFLOW, a quite common, or maybe probably the most common method, is still to use the recharge package. So you supply recharge somehow externally supplied to MODFLOW and apply it as a spatially distributed flux to the top of the model. So the most simple workflow would really be you take the raw precipitation or estimate it, then you apply a recharge coefficient, which you can then derive as a spatial recharge, where you can then derive a spatial recharge raster or grid. Then you import it into MODFLOW and calibrate the coefficient as a parameter, for example, with PEST through automatic calibration. Now, this is very efficient. It's not so much data consuming, but it comes along with a lot of uncertainty, because if you calibrate this coefficient as a parameter, it needs to reflect kind of all the different processes that are influencing the recharge. And this can become a quite non-unique solution, especially when you calibrate it in the same process, the hydraulic conductivity or also the riverbed leakage or the porosity. So if you increase the recharge a lot, you can increase also hydraulic conductivities, and you will probably achieve nearly the same calibration target and the same groundwater heads. So a very good example is one of the most common training examples for MODFLOW, which is called the flat water table example. So you suppose observations show groundwater heads 50 meters everywhere, but you have two models. Model A has a recharge of 250 meters per day and a higher hydraulic conductivity of 40 meters per day. Model B has a lower recharge with around 100 meters per day and a lower hydraulic conductivity. They both will produce roughly 50 meters everywhere. So the Nash-Sutcliffe efficiency, the NSE, will be probably close to each other, but the fluxes will differ a lot. So while for the first model A, Q1 will be quite high because you have a higher recharge and hence more water flowing in the system, you nearly halved the flow in the model B. So the Q2, so the flux in the second model will be probably only around 50% of the first model. And this has different effects, especially it impacts your well design projects or whenever you want to estimate not only groundwater heads, but you want to estimate fluxes or volumes. So another problem is the well field problem. You have the same heads, but you have quite different safe fields. So model, it's exactly the same example. You see here model green and model A in green, high recharge, high K. In blue, model B, medium recharge, medium K. And then C, yellow, low recharge, low K. And you see in the lower bottom that the predicted drawdown can differ quite significantly. For if you have a high recharge and a high K, the drawdown could be around 1 meter, quite low. And the more you reduce recharge and decay, of course, if you extract the same flux from your aquifer, you will predict a higher drawdown. Now, also many papers from John Doherty and others about uncertainty tell you the same story, of course, that you always have the problem with the non-uniqueness. You can balance out a wrong recharge with a wrong K, and you can not directly see this in your calibration targets or outcomes. But one solution, also one approach is, of course, you run many models with PEST and you do a lot of uncertainty analysis, which is also a very common and sophisticated approach. But there is a way to significantly reduce the uncertainty in your predictions that you do with your groundwater models. And that is if you use physics-based recharge values, for example, from a fully integrated catchment model like MikeShe. So you reduce the uncertainty in the recharge, and hence you also reduce the uncertainty in the hydraulic conductivity because you reduce the degree of freedom where you can vary your hydraulic conductivity during the calibration process. Now, a very short overview about MikeShe. MikeShe is, as I said, our fully integrated catchment model at DHI. It is really able to present all the processes that are relevant for the natural water cycle and the anthropogenic. So you have precipitation and snowmelt. You have vegetation-dependent evapotranspiration and infiltration. You can even include agriculture and simple to complex irrigation measures. We have a full TOD surface runoff and flooding model, which solves the San Fernando equation, the shallow water equation. You can also incorporate 1D rivers, including canals and complex control structures and logical rules, even sewers, 1D sewers, by coupling it to our software Mike Plus. It has its own soil water balance method. This is the one we will focus today, which solves simple methods or also the full Richards in 1D. And we have a full 3D groundwater model comparable to MODFLOW. But today, in order to use it as a very powerful soil water balance or groundwater recharge model, we will simplify the MikeShe a little bit. So we will not use the water quality module, we will not use the rivers and not the 3D groundwater model. Actually, today we also will not simulate irrigation. This will be another separate webinar. Just in case you're curious now, what does fully integrated catchment modeling with MikeShe mean? There is a webinar recorded also on demand, available from last year, which you can watch. It's roughly 1 hour. That shows you again a little bit more the functionality of MikeShe if you turn on the other modules and what it means if you really want to consider all the bilateral couplings and the mutual influences to really capture all the feedbacks that are happening also in the real world. Now, a quite powerful module here in MikeShe is the unsaturated zone module. You can see here you have really the option inside the graphical user interface to also model really the soil water retention curve and also the hydraulic conductivity curve, which is based on actual saturation of the unsaturated zone. That means if the moisture content goes down, of course, the hydraulic conductivity also goes down. And you have here parameters, and I will show you later a little bit how they influence it. On the upper right, you can see also the graphical user interface that allows you to even differentiate vertically in the depth which soil type you want to apply here from your conceptual model and how to discretize the computational numerical layers in your model. And this is quite significant because here we have a small example from southern Germany. You see in the dark blue line a measured groundwater head. And you have here different outcomes depending on different soil parameterization based on the soil type. Fun fact, in reality, the official public soil map indicated the brown sandy loam. And you can already see that the dynamics differ quite a lot from the real measured values, even if you assume that you have a lot of influence here inside a city. This was within a highly urbanized area. But we varied the values according to different soil types. And at the end, we could achieve with this fully integrated catchment model, including the 3D groundwater model, to show that especially the small dynamics, the small peaks during short precipitation events could represent it way better with a sandy soil parameterization. Now, also interesting, we have really a full 2D overland flow module that allows you to simulate also direct runoff processes, which is very important if you have a steep hill slope or very heterogeneous topography surface. For example, here you have a kind of mountainous region where you have strong runoff processes and that lead to focused recharge zones at the valley edges. So you can also capture that with MikeShe. We will not go into the details, but we also have a separate irrigation module that allows you to irrigate different parts of the model in different ways. You can even select here, depending if you have included a river, from where the water should be taken from. Should it be from the river, from a single well, from a shallow well, or externally supplied? How to apply it? You can choose between sprinkler, drip, and sheet irrigation. You have various options, and you can even set in the MikeShe model when it should irrigate. So depending on constraints within for the saturation of the unsaturated zone or for certain thresholds of the field capacity. Now what you can achieve and what we want to achieve at the end of this meeting, you see here another example. Now we are in northern Germany. You see I benefit here from many project references that we did in the last couple of years from my advisory background. You see here a quite heterogeneous topography in this catchment. You have here a little bit higher elevations with a high depth to groundwater, and then you have here the sandy valley area where you have a low depth to groundwater and actually a river flowing through. Now you see here the simulated groundwater recharge with the daily resolution. We start on the 1st of February and I will show you only 60 days because this already shows you a high dynamics. You will see here the color palette for positive values from light blue to dark blue into purple, showing you positive groundwater recharge rates. And you see from yellow over red to dark brown negative recharge rates. That means the evapotranspiration with a low depth to groundwater is exceeding the positive recharge rates. And you can see already how strong the dynamics is. You see how nicely the sweating front is climbing upwards, how it's constrained by lower conductive materials here, which you would also see in the hydrogeological and in the soil maps. And you also see here this strong dynamics where you have actually here a small rain event hitting the areas with the lowest depth to groundwater. That's why you have here positive peak values. Now, this is not only nice to see, it's really a fully calibrated model. We achieved here quite extraordinary good calibration, and we also matched not only the several groundwater heads in this area quite good, but also the outlet of the river discharge. So you can really trust here the water balance. I would like to go with you in this example a little bit more in detail. I apologize for the German legend here, but let's focus here on one station. We also use this example now for an upcoming publication, and we wanted to see what the changes of the porosity mean for the actual dynamics in the simulated groundwater heads. And we varied the reference run with a saturated soil moisture of 0.3 by 10 and 30% plus and minus. And you can see that the averaged groundwater recharge in millimeter per year already is influenced quite significantly. So the lower the porosity, the faster the water percolates downwards, and the higher is the actual recharge for your model. Looking at the groundwater recharge rates as the time series, you see that with the lower porosity, minus 30%, you have the strongest dynamics, stronger peaks, and you also achieve higher values and lower values. And the lower, the higher the porosity, the more water you keep in the top soils, you provide it or offer it to the atmosphere for actual evapotranspiration, and therefore you get more buffered values and also an overall lower recharge in the long term. Looking at the resulting groundwater heads, you can see here the green is the reference run, black actually the measured ones, which differ also from our reference run because we needed to do some simplifications for this sensitivity analysis. But what is nicely to see, and this should be a takeaway for you, you can see this time shift. That means the lower the porosity, the earlier and the stronger are the peaks in the simulated groundwater heads. So it's not only the porosity or the hydraulic conductivity in your groundwater model that can affect or lead to a certain time lag and change in dynamics. It could also be introduced already through your recharge rates. So you see the higher the porosity, the longer it takes until you achieve or you reach the lowest and the highest values, simply because the water is hold back, maintained longer in the unsaturated zone, and it takes more time to percolate downwards. You could simulate the same effect by reducing the hydraulic conductivity. So reducing the hydraulic conductivity or increasing the porosity can lead to the same effects in your simulated groundwater recharge rates. We have another example to show you also how it is reflected if you have different depths to groundwater. So green, large depth to groundwater, blue, middle depth, average depth to groundwater, and red, low depth to groundwater with the strongest dynamics. You vary here in such a low lying area from positive to negative values quite quickly. The higher the depth to groundwater, the more buffered are your recharge rates. And if you have a high depth to groundwater of a couple of meters, you see this typical patterns that nearly indicate already to look like a simulated groundwater time series. We have a quite powerful water balance calculator tool, which I will show you at the very end, that helps you to summarize and condense a little bit the spatially distributed recharge rates into meaningful diagrams. You can do this for each component, as you can see here. You can also see how here from March to May the snow melts down while the snow is accumulating in the winter months. And of course, you can do this also summarized in a more high level. This is more of interest for you if you want to see, for example, the overall catchment water balance, mainly focusing on the most relevant processes, or you want to assess a little bit possible groundwater abstraction permits. Now, turning all these modules on, we did this for one of the most important and largest post-mining sites here in northwest Germany, where we are working for our client for many decades. They wanted to do us an irrigation demand prediction and also simulate the groundwater recharge until 2050. We did that with different climate protection scenarios, which was also quite interesting for us. You see this post-mining area is highly influenced by the red dots, which are showing wells in a FEFLOW model. And they wanted to know how much water they need to abstract in the upcoming decades to allocate the costs for new pumping stations. And you can see with the climate projection scenarios, these indicate at the moment falling groundwater trends due to higher evapotranspirations and higher hotter summers, which is important for their financial planning. Now, why we think our groundwater recharge rates are more sophisticated than others. As I told you, we normally apply MikeShe as a fully integrated catchment model, including all the modules. So we are really able to simulate all the processes and close the water balance. Another example I can show you here with a small rewetting study in southern Germany again. It's a very local scale model, but this shows you what is actually possible with the MikeShe model. We focus here in this low-lying degraded peat area, and I focus on the station A09. Here we have a small river, actually with a discharge gauging station, which we were also able to use for plausibilization and calibration purposes. Now you see here of A09 the depth to groundwater in black, the measured one, and in red the simulated ones. So in our model, including the 2D overland flow, the groundwater head can actually also rise above ground, like it was measured here from time to time. And we really nearly perfectly represent the drawdown in the groundwater. Also the rise, again, for short-term precipitation events, nearly match perfectly. And also a strong drawdown during the very hot summer here in 2022 is completely reflected. We nearly achieve the lowest values, and you see that you can simulate groundwater heads with extremely high resolution and reliability. Of course, depending also a little bit on the spatial resolution that you want to achieve in your MODFLOW or FEFLOW model. But MikeShe is able to provide you the necessary recharge to achieve this. In order to ensure that the water balance is really plausible and sophisticated, we calibrated here also for the discharge of the river. You see here the discharge. The dots are the typical representation of measured values in the MikeShe graphical user interface, and the continuous line are the simulated ones. And you can see here that even small discharge events are perfectly captured by the model. We achieved here a mean absolute error of 2 liters per second, which indicates a correlation of roughly 88%. So when you do this, if you do the fully integrated catchment model and you calibrate the groundwater heads as well as river discharges, you are really producing a very reliable groundwater recharge rate, which is probably with an uncertainty of less than 10%. Now, this fully integrated catchment concept is also applied to whole Denmark. You can see here a short screenshot, and you can also visit the website if you want to see it. It's quite advanced. They simulate here groundwater heads, river discharges, and groundwater recharge rates for whole Denmark. They have split it up in 4 to 5 models, but you can see MikeShe, due to the different modules that can run on their own time step, it's possible to simulate also very large areas in a physics-based manner. Also in the US, we have a quite active user community, especially around South Florida. Also, it's for South Florida Water Management District. It's an important tool in their daily work, because you have here a lot of canals that drain the groundwater and keep the urbanized areas dry, especially during hurricanes or strong rain events. And there you have a lot of river groundwater interactions, which is one of the key strengths of MikeShe. And you can see also here that you're able to really calibrate also observed discharges and water levels perfectly in the model, even with complex control structures. Now, when MikeShe stands out for recharge, especially if you have a partially steep terrain and low conductive topsoils, and you can expect a considerable 2D overland flow. Of course, the 2D overland flow solver that uses a finite difference scheme is a key strength. If you want to include simple to complex irrigation activities, it's also quite a big differentiator from MikeShe to do that. And pretty often MikeShe is taken into account if other tools were failing in the past. That means you were maybe doing a mining environmental impact assessment and you used MODFLOW or FEFLOW and you used a too simplified recharge. It could be that an external reviewer is rejecting your recharge approaches, and then pretty often we come into the discussion to produce more defensible recharge rates for the model, which are then accepted by external reviewers more probable. So if you want to benefit from an intuitive graphical user interface that guides you through the model build, then this is another good reason for MikeShe. You can leverage a lot of prepared scripts and workflows that enable a model build actually in less than 2 days. I will show you later. Actually, if you get used to the workflow, it's probably less than 1 day to build the model and to run it another day. You can benefit from a 24-hour support service if you run into problems, so you do not need to solve them yourself. And really, we have a global engaged community that advances workflows and ensures long-term efficiency. Now, talking about the fully integrated catchment concept of MikeShe, it's really unique if you want to simulate groundwater, surface water, and evapotranspiration in one system. If you want to consider a bilateral exchange in both directions, especially 1D rivers and a full 3D groundwater model, which is not the focus today. And if you want to include complex 1D rivers or pipes, including structures with logical operation rules. You can actually simulate contamination traveling through overland flow, groundwater, and rivers from one component to the other as you want. So this is one of the key strengths also, and maybe unique from MikeShe. And if you want to apply physics-based approaches on a regional scale over many years. And a big benefit is really the powerful graphical user interface. Even if it looks a little bit outdated, it takes away a lot of problems and prevents you from inserting wrong values and helps you through this very sophisticated and advanced modeling workflow. That's it with the first introduction, and we will now continue with how we can integrate the MikeShe results into MODFLOW and FEFLOW.